We can see that we have a positive and a negative charge. So when we try to find the force on charge A because of charge B, we know that it will be to the right. To find the magnitude of that force, we use Coulomb's law. F equals K Q1 Q2 over R squared. K we find on the reference table, 9.0 times 10 to the 9 newtons meters squared per Coulomb squared. Be careful with the prefixes. Q1 is 5.0 microcoulombs, so times 10 to the negative 6 coulombs. Q2 is negative 2 microcoulombs, so I'm not going to write the negative sign because we only use the signs to show that it's attractive, to determine that it's attractive. But micro is times 10 to the negative 6. And the distance between them is 30 centimeters, so 0.30 meters. And don't forget to square it. Putting this into the calculator, I get 1.0 newtons. But let's remember that force is a vector, and so I should write in the direction, which in this case is to the right. When asked what is the force on charge 2 because of charge 1, we could redo Coulomb's law, just swapping out which one we multiply first, Q1 or Q2. But we should realize that this is really just an example of Newton's third law. For every force, there's an equal but opposite force. So my answer to B1, without doing any calculation, is 1 Newton to the left. And we knew that because of Newton's third law. To find the rate at which charge 2 will accelerate to charge 1, I'll use Newton's second law, F equals ma. The force was 1 Newton, and the mass of charge 2 is 0.15 kilograms, giving me an acceleration of 6.7 meters per second squared. That's the rate at which charge B will accelerate initially. It's strange in this question that we're asked to compare the amount of time it would take B to reach A to 300 milliseconds. 300 milliseconds must be meaningful. And the 300 milliseconds comes from using UAMs. The distance between the two particles is 0.30 meters. Its initial velocity is 0, so 1/2 will take the acceleration that we found in the last part. And we see the time we get is 0.30 seconds, which is 300 milliseconds. Now this relies on charge B accelerating towards charge A at a constant 6.7 meters per second squared. But that's not the case here, because as B approaches A, the force of attraction grows. And so it will actually take less than 300 milliseconds until it reaches A.